Dear students, today I am going to take a discussion of reservation table problem. So how we can solve reservation table problem? For that you will be given with a reservation table like this, which consists of a number of stages and a number of clock cycles. Here there are 3 stages and 8 clock cycles. Okay, so the problem is to find the forbidden latency, permissible latency, then draw the state transition diagram and so on. Okay, so we can see how we can solve these problems using the reservation table. So the first problem is find the forbidden set of latency. So let's see how we can calculate the forbidden latencies. So in order to find the forbidden latencies, check the distance between two check marks in the same row of the reservation table. For that, consider the reservation table, which consists of stage 1, stage 2, and stage 3. In order to find the forbidden latency of stage 1, we need to find the difference between the check marks. Okay, for that, here the check marks are present in clock cycle 1, 6, and 8. So the forbidden latencies are 8 minus 1, which is 7, and 6 minus 1, which is 5, and 8 minus 6, which is 2. And for stage 2, the forbidden latencies, the check marks are present in the second and fourth clock cycle. So 4 minus 2, which is 2. And for stage 3, the forbidden latency is 7 minus 3, then 5 minus 3, and 7 minus 5. Okay, so we find the forbidden latency like 2, 4, 5, and 7. Multiple entries of a particular forbidden latency is not permitted. And forbidden latency means the latencies which make collision, and permissible latencies are latencies which does not make collision. So in order to find the permissible latencies, we need to find the latencies which are not in forbidden latency. So please check our forbidden latency. Our forbidden latency is 2, 4, 5, and 7. Then our permissible latencies will be 1, 3, 6, and 8. 8 will not be there because the forbidden latency, the maximum value of forbidden latency is 7. Hence, the permissible latency must be less than 7. So, our permissible latencies will be 1, 3, and 6. Okay. Then the third problem is find the collision vector. So, let's see how we can find the collision vector. Generally, collision vector C is represented as C is equal to Cn, Cn minus 1 up to C2, C1. And for forbidden latencies, we mark the value of CAS 1, and for permissible latencies, we mark the value of the collision vector CAS 0. So the collision vector of the above questions will be 1, 0, 1, 1, 0, 1, 0. It's very simple. You just mark 1 for forbidden latency values and mark 0 for permissible latency value. Here, why C7 is here? Because 7 is the maximum value of forbidden latency. So C7, C6, C5, C4, C3, C2, and C1. Okay. Then for forbidden latency, we mark 1, and for permissible latency, we mark 0. Okay. Then the fourth question is how to construct a state diagram. In order to construct a state diagram, the collision vector is essential. So state diagrams can be constructed to specify the permissible transitions among successive initiations. The collision vector corresponding to the initial state of pipeline at time 1 is called the initial collision vector. Okay. So the initial collision vector, we already find the initial collision vector. This is the initial collision vector. And using the initial collision vector, we can find the state diagram, and a number of procedures are to be followed. The procedure is as follows. The first procedure is start with the initial collision vector. We have already find the initial collision vector. And the second procedure is for each unprocessed state, for each bit I in collision vector, which is 0, do the following. So find the values of collision vector which has value 0, and for each value 0, do the following procedure. Okay, so again, please consider the collision vector. We have 0 in the 6th position, then 3rd position, and on the 1st position, isn't it? Okay, so only in order to find the state diagram, we only need to find the collision vector values which are 0. Okay, for each value 0, we do shift the collision vector right by I bits. Okay, if we have 0 in the first bit, then shift the collision vector by 1 bit. Okay, then drop I rightmost bit, and we need to drop the rightmost bit corresponding to the number of bit that we shifted. Then append the corresponding number of zeros to the left. Okay, and logically or that particular value with the initial collision vector. And the final step, if the result in a new state, then form a new node for the state and join it with the node of collision vector by an arc with a marking I. This shifting process needs to continue until no more new states can be generated. Okay, from the initial collision vector, we get a number of other states, other vectors, and we do this process until no more new states can be generated. Okay, this is a right shift register. The next state can be obtained with the help of a p-bit shift register. Okay, this is a p-bit right shift register. Each 1-bit shift corresponds to increase in the latency by 1. In order to draw the state transition diagram, here it is the initial collision vector. Okay, here 1 indicates collision and 0 indicates no collision. So 0 is present in the first position, 3rd position, and the 6th position. So 1-bit shift, 3-bit shift, and 6-bit shifts are necessary. Okay, 1-bit right shift, 6-bit right shift, and 3-bit right shift, which creates new states. Okay, the next state is obtained by bitwise sorting the initial collision vector with the shifted register. So I have already said 1-bit shift is needed, 3-bit shift is needed, 6-bit shift is needed, because there are 3 zeros which is in the position 1 between 1-bit position, 3-bit and 6-bit position. So corresponding to the number of zeros, based on the position of the zeros, we make right bit shifts. So first bit, 1-bit right shift is performed here. A bit is shifted to right and append a 0 on the left side. Okay, and this value is ORed with the initial collision vector. So we get our next state as 1 1 1 1 1 1 1. Okay, So our state diagram will be like this. So we have already found out the next state, and for 3-bit and 6-bit shift, we get the collision vector. We get the state as 1011 Okay, and we again do the, if there are a number of zeros in the new state, then we do the same operation again and again until there are new states are generated. Okay, so there is 3, 6, and 8 plus. If we do a shift 8 plus shift in the new state, then we get the same initial collision vector. And if we do a 8 plus shift in the initial collision vector itself, we get the same initial collision vector. That is represented as 8 plus is leading to the initial collision vector in both the states. Okay. So then 3-bit shift leads to the 3-bit and 6-bit shift are performed. Why? Because here the 0 is present on the 3rd and 6th position. Third and 6th position. So 3-bit and 6-bit shift of this particular state is required. And in the state, there is no shift is required because there is no zeros. Okay. So like that, we get the state diagram. And we need to find the simple cycle and greedy cycle. So simple cycle is a latency cycle in which each state is encountered only once. Okay. If there is a particular state encountered only once, then it is a simple cycle. Each state is encountered only once. Then complex cycle consists of more than one simple cycle in which, and greedy cycle means a simple cycle is greedy if each latency contained in the cycle is the minimal latency from a state in the cycle. Okay. A simple cycle is a greedy cycle. A greedy cycle is a simple cycle. And if its latency is a minimal latency. Okay. A greedy cycle is one whose edges are all made with a minimum latency from their respective starting states. Greedy cycle is simple and average latency is lower than all the other simple cycles. Okay. A good task initiation sequence should include the greedy cycle. Then collision-free scheduling reduces to finding greedy cycles from simple cycles, and one greedy cycle will yield to minimum average latency. So in order to find the minimum average latency, one of the greedy cycle will lead to, with a minimum value, lead to the minimum average latency. So here we got a number of latency cycles. So we get the latency cycle like 8 is a latency cycle that which makes the latencies which makes some cycle. Okay, that is 1, 8. 1 and 8 make a cycle. Then 3 and 8 make a cycle. Then 6 and 8 make another cycle. Then 3 is a cycle. Then 6 is a cycle. So these are the set of cycles in this particular state transition diagram. Okay, the latencies which make some cycles. So there are a number of cycles here, and in order to find the simple cycle, if the state is not repeating, that particular cycle is simple cycle. So from the latency cycle, we made some simple cycles where the states are not repeating. Each state appears only once. So the simple cycles are 3, 6, 8, 1, 8, 3, 8, and 6, 8. Okay. Why we ignored 1, 8, 6, 8? Because 8 is appearing twice. Okay. Then greedy cycles. From the simple cycle, the minimum value we take is greedy cycle because from different starting states. Okay. 3 and 1, 8 are the greedy cycles. Greedy cycle is a simple cycle with a minimum value. Then here, the minimum average latency is 3. And in order to find the minimum average latency of this particular greedy cycle 1, 8, we need to add 1 plus 8 divided by 2. We take the average of this particular cycle. Okay. Like that, we can calculate the minimum average latency. And here 1 plus 8 divided by 2, which is 9 divided by 2, which is 4.5. So the minimum value among that will be taken as the minimum average latency. Hence, the minimum average latency will be 3. Okay. So here is the end of reservation table problem. So I hope you all understand reservation table problem and how we can find the forbidden latency, permissible latency, how we can draw a state transition diagram using an initial collision vector. Thank you.